Today we will discuss section 3.4, the mole. And as you can see on the screen, there are lots of cute little images of moles. If you've ever seen a mole in real life, you'll know they're really not all that cute. But our mole in chemistry is a little bit different, so let's get started. Moles in chemistry are a counting unit similar to a dozen, except they're much, much bigger. Moles are used to count atoms and molecules. This next piece of information is very important, so I suggest you highlight it in your notes. 1 mole is equivalent to 6.022 times 10 to the 23rd particles. And when we use the term particles, that really is a generic term that incorporates several different types of things. Particles can mean atoms if we are talking about an element. Oops. And that would be anything on the periodic table, like iron or sodium or sulfur or something like that. However, if we had something like water, it wouldn't make sense to say we have a certain number of atoms of water, because it's not an element, it's a compound. So we have two other terms that we use in place of atoms if we're talking about compounds. If it's a molecular substance, then we use molecules. And remember, something molecular will be two nonmetals. As we mentioned, water. It would make much more sense to say you have a molecule of water rather than an atom of water. But when we talk about ionic substances, a slightly different term is used. We use the term formula unit. And believe it or not, when you talk about formula units in chemistry, yes, they are actually abbreviated FU. An example of a substance that would require formula units would be something like table salt. So the term particles is okay, but we will always try to use the more specific term of atom, molecule, or formula unit. Yesterday in section 3.3, we discussed formula weights and molecular weights. I like to just call these numbers that we add up from the periodic table the molar mass. And this blank grams is molar mass. And you may want to put a reminder for yourself that we always get this information from the periodic table. Very important that you keep the proper numbers with the proper units. It's not a mix and match kind of thing. So as we will be using dimensional analysis today, make sure you keep the number 1 with moles. I shouldn't ever see 1 gram anywhere in your calculations. Make sure you keep 6.022 times 10 to the 23rd with either atoms or molecules or formula units. We would never want to use such a huge number with grams, because that just wouldn't make sense for us to be measuring anything that large in terms of mass. And grams, again, that number is going to vary, but you do obtain it from the periodic table. Now when we say that a mole is a counting unit, I like to compare it to a dozen. When you say a dozen, the number 12 just pops in people's heads. You can have a dozen eggs, a dozen donuts, you can have a dozen people, a dozen pencils, a dozen notebooks, 12 of anything. Well, when you say a mole, we like to think of 6.022 times 10 to the 23rd of anything. Now when we look at that number, it's really hard for us to understand just how crazy wicked large it is. If you expanded that out, instead of using scientific notation, it would look something like this. And that's a lot of zeros. When you look at this number, and if you ask somebody how much it is, I mean, the answer is really just a lot. Because if you had 1,000 of something, 1,000's a lot. But certainly a million is a much bigger number. Well, can we even really understand what a million is? A million only goes to that spot right there. A billion would be here, and a trillion would be here. So it's kind of crazy how big this number is. It's like having like a trillion of something. So the point is it's very large. This number is also known as Avogadro's number, named for the Italian chemist Amedeo Avogadro. It looks kind of creepy if you ask me. But you should know it as Avogadro's number. It's a little quicker than saying 6.022 times 10 to the 23rd. Now just some common examples for you to illustrate how big this mole's number is, or Avogadro's number is. If you had a mole of eggs, 6.022 times 10 to the 23rd eggs, they would fill all of the oceans on Earth 30 million times over. It would take 10 billion chickens laying 10 eggs per day over 10 billion years to lay a mole of eggs. Here's a little different slant on it. If you had a mole of pennies, so 6.022 times 10 to the 23rd pennies, and you started distributing those pennies to people, one for you, one for you, one for me, and you distributed them evenly amongst all the human inhabitants of Earth. Each man, woman, and child would have enough money to spend $1 million every hour, day and night, and still have over half of it unspent at death. So we're talking a big, big number. Now the mole is so central to chemistry that we certainly put a lot of importance on it. There's actually a National Mole Day Foundation, which has different themes every year. And National Mole Day is celebrated on October 23rd, 10 to the 23. And like I said, they come up with a different Mole Day theme every year. One year it was Rock and Mole, and they're all very punny, so you're either going to love them or hate them. And some are better than others. In 2007, they were playing off the James Bond theme, and they went with Double Mole 7. Moles are forever. So, yeah, they're a little bit of a stretch, but they can be kind of entertaining. We will be celebrating Mole Day as well. And to help us do that, we're going to take a mole pattern, and this is an extra credit opportunity you will have, and see how creative you guys are at coming up with good mole puns. Now, some past moles that we've had submitted include guacamole, very nicely made, cute little hat. Rock and Mole, this was Moldana, love the little glasses prop. Superheroes seem to be a very common theme, so we have had the Three Molesketeers, and one of my favorites, Captain America. Very nicely made. So, something to look forward to. We're now going to take a look at your example sheet, the class examples that you have. And as we go through these, keep in mind the sub can always pause the video and rewind if you have questions, if you didn't follow something, or you can just pause it and you guys can clarify with each other if you need to. So I'll do a couple with you, and then you guys can try one for as an example as well. So number 1, how many formula units are present in 6.56 moles of barium chloride? Now first of all, before you get all crazy with your calculator, make sure you understand when you see barium chloride, we have to use nomenclature rules to obtain the correct formula. I get many students that read barium chloride and they write BaCl. But those are the two ions, but that's not the correct formula. We have to rely on our ionic nomenclature rules to help us write the formula properly. Barium, which is an alkaline earth metal, has a +2 charge, and chlorine, which is a halogen, has a -1 charge in compounds. And so if you do the crisscross, the formula is not going to be BaCl, but actually BaCl2. So you can solve mole calculations using some of the dimensional analysis skills that we learned about in Chapter 1. First rule of dimensional analysis is you always want to write your given information. So I'm going to start with 6.56 moles of barium chloride. Now, given the information on our previous slides, we had 1 mole, just for review here, equals 6.022 times 10 to the 23rd. Sorry, the writing's always bad at the edge of the screen. I'm not quite sure why. And that equals blank grams, the molar mass from your periodic table. Now, you have 3 pieces of information that you can use to make a conversion factor. And unlike some of those horrible, long conversion or dimensional analysis problems that have, 8 steps or something crazy like that, these can all be solved in just 1 step. And I really, really stress to pay attention to the units, because that a lot of times is your key, as in any dimensional analysis problem. So if you are given moles, we want to put moles on the bottom. And as you're learning this, it might be helpful to just start with your units and then fill in your numbers as a secondary piece of the process. So moles need to go on the bottom. And I look at my given information, and 1 is the number that goes with moles. And no, I haven't misspelled moles. In chemistry, moles is actually abbreviated MOL. I know it's so hard to write that extra E. Just make sure that you understand it's moles and not molecules. So anyway, we've got moles, they're gone. Now we want to change it to formula units, and formula units is a type of particle, which means we need to use Avogadro's number. So 6.022 times 10 to the 23rd formula units, and then we just need to crunch it out on our calculator. So everybody should be calculating these right along with me. 6.56 times 6.022 times 10 to the 23rd, and if we round it to 3 significant figures, we would get 3.95 times 10 to the 24th. Formula units is a good label, but in chemistry it's always helpful to label the substance as well, so formula units of barium chloride. If your exponent is off, let's say you get 10 to the 25th, it may be the way that you're entering Avogadro's number on your calculator. So I'd encourage you to make use of the EE button, the second comma, or the button right above the 7 on most graphing calculators. It's just kids seem to make fewer errors if they use that button. If you like the times 10 with the caret, you've got to really be careful with your parentheses so that you don't end up with an error. Let's take a look at another one. How many moles are present in a 267 gram sample of lithium iodide? And again, I'm just going to start by writing the formula before we begin. Lithium iodide, lithium is Li plus 1, iodide is I minus 1. And then to start our dimensional analysis process, we'll start this time not with moles but instead grams. So 267 grams LiI. And if we again take a look at our labels, we have grams, we want to cancel out grams. So I know that's going to need to go on the bottom. I am looking to find moles, so I'm going to put moles on the top. Be very careful as you fill these in. Sometimes people see moles and they put Avogadro's number on the top. And really make sure you're keeping the proper number with the proper label. So Avogadro's number doesn't go with moles. It goes with things like atoms or molecules or formula units. So moles, for our purposes right now, is always just labeled with a 1. The grams number is determined from the molar mass on the periodic table. So grab your periodic table and add up the masses for lithium and iodine. Oops, I don't know why that disappeared. And when I add up this molar mass, I've got a slightly different version of the periodic table at home with me here. And lithium I'm showing as 6.941. And my iodine might be a little bit different than yours, but it should be roughly the same. I have 126.90447. And that would give me an approximate molar mass of 133.84547. At least approximate in the sense that it might be a little different than what you have in front of you with your periodic table. And then to solve, remember we multiply across the top, divide by the bottom, so essentially 267 divided by that molar mass. And to three significant figures, we should get 1.99 moles. Abbreviation for moles, MOL, and again, always a more complete answer if you include the formula of whatever it is you're working with. At this point, we'll take a look at problem 3. What is the mass of 5.21 moles of dinitrogen tetroxide? I'd encourage you to have the sub pause the video at this point and go ahead and try this one on your own. And when everybody's finished, you guys can start it up again and we'll see how everybody did. Alright, hopefully we've had a chance to try this one. And in this problem, again, always start with determining what the correct formula is for whatever substance it is you're working with. Dinitrogen tetroxide is a molecular substance, and we want to make use of our knowledge of our prefixes in this case. So dinitrogen would be N2, and tetroxide, or tetraoxide it's sometimes written, is O4. And so we start with 5.21 moles of N2O4. We want to convert this mass, would be grams that we're looking for. So I need 1 mole on the bottom. And then I know I want to find grams. And for this one we need a molar mass, which again is determined from the periodic table. So 2 times 14.0067, the atomic mass for nitrogen, plus 4 times 15.9994, the atomic mass for oxygen, gives us a molar mass of 92.011 grams. And to solve for your answer, 2.51 times 92.011, we have 3 significant figures. And so our answer is 479 grams N2O4. Now, those 3 problems are considered to be the pretty run-of-the-mill standard mole conversions from grams and a type of particles and moles. However, there are a few kind of extension type, a little bit deeper level type problems that you'll be expected to know when you get to the textbook problems and online problems as well. So let's take a look at 2 more. Number 4, determine the total number of atoms in 195 grams of propane. Propane would be C3H8. And at first this is going to appear like a regular problem we've done before. 195 grams is what we would start with. And we would use our calculators to find the molar mass of propane. So 3 times the mass for carbon, plus 8 times the mass for hydrogen. And we get 44.0962 grams. So that would go on the bottom. Now, many students know they need to use Avogadro's number somewhere, they're just not sure how or where. As you're looking at this problem, we know that 44.0962 grams is 1 mole, and in 1 mole there is Avogadro's number of particles, 6.022 times 10 to the 23rd. Now, the problem comes in with how you label this Avogadro's number this time around. Since it is asking for atoms in the problem, it is common for kids to write atoms. But if you think about propane, just like we talked about water previously today, Water doesn't exist as atoms. It's a compound, so it's going to exist as a molecule since it happens to be made of two nonmetals. So I'm going to label this as molecules, which is a step in the right direction, but not quite our final answer yet. It asks for a number of atoms. If you look at C3H8, it contains 3 carbon atoms and 8 H atoms. So for each molecule, we know that there are 11 atoms. So in this problem, we have one extra step of multiplying by the total number of atoms in one molecule. If you crunch out that number, 195 times 6.022, 10 to the 23rd, times 11, and divided by 44.0962, you should come up with 2.93 times 10 to the 25th atoms. Some students are confused by this extra step, and I'd encourage you to think about it this way. If you had 100 cars in the parking lot and you were asked how many tires are there, and of course we'll ignore the spare tire, but you very quickly all of you would say if there's 100 cars that there would be 400 tires because each car has 4 tires. In a problem like this, the first conversion helps you go from grams to a number of molecules, but then you have to multiply it by 11 because in this case, for propane, each molecule has 11 atoms. So that's why there's that one extra step. We'll finish up this section with one more problem. Number 5, how many carbon atoms are present in 3.56 milligrams of C6H12O6, a sugar in this case? Now, this problem has 2 kind of complicated parts. First of all, it's not a real big complication, but we have been doing all our problems so far with grams. So if you're given milligrams, we need to make sure that we convert this to grams first. So 1,000 milligrams in a gram. Then from there, we can cancel out our grams by adding up the molar mass of glucose. 6 times 12.011 plus 12 times 1.079 plus 6 times 15.9994, and you should get a molar mass of 180.1572 grams. Now that would be for 1 mole. You could write 1 mole here. If you wanted to, you could go right to Avogadro's number. Either way is fine. But in 1 mole, there's going to be 6.022 times 10 to the 23rd molecules. And again, I chose molecules because this is a molecular substance made of nonmetals. It's not an element, so I don't want to use atoms. It's not an ionic substance, so I don't want to use formula units. So I picked molecules. This calculation so far, if I stopped here, would give me the total number of molecules in my sample, of glucose molecules. But it doesn't ask about that. It asks specifically about carbon atoms. Now in the previous problem, we multiplied by 11 because there were 3 carbons and 8 H's in propane for a total of 11 atoms. This time I'm not going to add up all the little subscripts because it doesn't ask for the total number of atoms. It only asks for a specific number of carbon atoms. And when I look at the formula, I can see that for every 1 molecule, there are 6 carbon atoms. So this time around, instead of multiplying by 11, we end up multiplying by 6. So if you check your calculation, type it in here as well. So you guys can check my math here. I'm coming up with 7.14 times 10 to the 19th carbon atoms. So that's the end to the first section for today, 3.4 on moles. At this point, you can pause the video, take a quick stretch break, come on back, and we'll finish up with 3.5. Section 3.5 is on empirical and molecular formulas. And it's very closely related to our first section for today, 3.4. And so you'll see quickly why we had to do moles in order to understand this section. So first we'll start with the difference between empirical and molecular formulas. An empirical formula, which will be abbreviated EF on the following slides, is the lowest whole number ratio of elements in a compound. We talked about this briefly in Chapter 2. It's always reduced or simplified in terms of the subscripts, and an example would be butane, which is the compound C4H10. If we wanted to write the empirical formula for that, we would simplify those subscripts and get an empirical formula of C2H5. A molecular formula, on the other hand, shows the actual number and type of atoms in a real compound. And it's a little bit tricky because this one may or may not be reduced. A substance that is real that you probably have in your house is hydrogen peroxide, H2O2. And if you look at that formula, that's a real compound. It contains 2 H's and 2 O's, so we call it a molecular formula, and it's not simplified or not reduced. If you think about water, however, H2O, which is also a real compound, that one has 2 H's and 1 O, so it's a 2-to-1 ratio, and it is reduced or simplified. So the important distinction is empirical is always reduced, and a molecular formula represents something that's actually a legitimate real formula. We're going to discuss the steps used to determine an empirical formula. And usually what you want to watch for in the problem is that you're going to be given percent composition data. So if you are trying to keep track of all the different math calculations in this chapter, you'll want, if you see an unknown compound is 20% carbon and 50% this, and if you're given percents, it's this type of calculation. The steps that we perform is the first thing we do is assume a 100-gram sample. And for us, that just means we'll be able to change the percent to grams. Once we have grams, we can convert it to moles, just like section 3.4. And since we want to get the formula to be the lowest whole number ratio, we'll divide by the smallest number of moles that we obtain. And then at the end, we want to make sure our subscripts are whole numbers. We'll be seeing some examples where you do that step 3, and then there's an additional step you have to do to make sure they are whole numbers when you're done. A very handy poem for you. And I encourage you to memorize this because there are a lot of calculations to keep straight in chapters 3 and 4. And when we have our next exam, you'll want to kind of have this in the back of your mind. But it has a little nice ring to it. Percent to grams, grams to moles, divide by small, multiply till whole. And if you can just kind of have that in your mind, it's a good thing to know going into the test or going into your homework. So let's take a look at an example. We have a compound that's 25.9% nitrogen and 74.1% oxygen. And the question is, what is the empirical formula? So our first step, percent to grams. So I'm going to start by writing 25.9, but instead of percent, I'm going to write grams of nitrogen. And I'm going to do the same thing for the other element, 74.1% oxygen. So first step's easy, percent to grams. Then we do grams to moles. On your periodic table, 1 mole of nitrogen has an atomic mass of 14.0067. And oxygen has a mass of 15.9994. when we divide for the first answer, we get 1.85, and for the second, we get 4.63. So again, our steps are percent to grams, grams to moles. I've now found my 2 mole numbers. The next step is to divide by small. So we look at our 2 answers, and we have 1.85 and 4.63, so the smallest one is, smaller one is definitely 1.85. And when we do that, we get 1, and for the second one, we get 2.5. Now, the last step, ensure all the subscripts are whole numbers, or in the poem, the multiply till whole. We usually do not make it a habit of writing formulas as n. Well, first of all, we never write the ones, but this is just for an example. If we look at the subscripts here, I would have n1, o, 2.5. And we need to get rid of that half. One of the tricks I showed you when we were balancing equations is that if you can get the coefficients to balance with a half in there, and you want to get rid of that half, you could do so by multiplying by 2. So in this case, since I have 2.5 as my moles, I want to get rid of that half, so I'm going to multiply the whole thing times 2. And you have to do that with both subscripts. So that means our empirical formula is N2O5. And you want to check when you're done, are those subscripts the lowest whole number ratio possible? And 2 to 5 can't be simplified any further, so it would be correct. Another example, naphthalene, a stinky compound found in mothballs. I don't even know if you guys even know what mothballs are anymore, but when we used to have old, cool, antique cedar chests, and you'd have cool heirlooms and clothing and other keepsakes in there, you didn't want them to have holes in them, so you'd put mothballs in there to keep away those moths. And they smelled really bad. I'll have to get some for you so you can see. They contained 93.75% carbon and 6.25% hydrogen. We need to find the empirical formula. So again, 93.75 grams carbon, 6.25 grams hydrogen, and we want to change grams to moles. So 1 mole of carbon is 12.011 grams, and 1 mole of hydrogen from your periodic table, 1.0079 grams. If you go ahead and do the dividing, you'd get 7.8. I'm going to carry a couple extra sig figs here. 7.805 and 6.20 or 6.201. So once we get our mole answers, we're going to divide by the smallest one, 6.201. And clearly the hydrogen will be 1. And the carbon, you get 1.25. Now, sometimes students will think, well, that's just close enough to 1 and I'm going to round it. But if you think about 0.25, it's really the fraction 1/4. So we're looking at carbon 1 1/4 or 1 1/4 H1. So we want to get rid of that fraction again, and this time instead of having a half, I have a 4th, so we'll multiply by the reciprocal by 4 to get rid of that, and that means our empirical formula is C5H4. Now keep in mind, as you're working on empirical formula problems, sometimes you'll have the added step of having to multiply by 4 or multiply by 2. If we had divided and it had come out to really whole numbers or numbers very close to whole numbers, like If it had been 1.99 and the other one had been 1, well then it's a 2-to-1 ratio, and you don't have to do this extra step. It's just if you end up with a fraction after you've divided by the smallest number, then you do need to do this additional step. Now, one of the reasons empirical formulas are important, some kids, just find this to be a lot of number crunching, and the reason why it's an important process. If we have a substance that's an unknown, it can be analyzed using a mass spectrometer, and you can do different types of spectroscopy analysis on the sample. You can determine what elements make up that material, and you can actually put in a sample and it'll give you a readout of this type of information, like the percent composition data we're being provided. From that, you can find its empirical formula, and then in the next process we're going to talk about, where we find and determine molecular formulas, then you can actually get an actual identity on the unknown compound. And if you look in my stockroom and 95% of the substances are white granular or white powdery substances, this process is important because it'll help you determine the difference between something that's pretty harmless like salt or sugar and something much more dangerous like a poisonous cyanide salt. So our last part for this section is determining molecular formulas. This process, if you understand the empirical formulas, you will find to be much more straightforward and much shorter as well. To find the molecular formula, the first thing to remember is that the molar mass will always be given. Sometimes kids look at the steps and it says to use molar mass, and they kind of panic because they don't know what the real formula is for the compound, so how in the world are they supposed to find the molar mass? Well, just relax, that'll be provided in the problem. So the calculation you need to complete is you need to take that molar mass that's provided and divide it by the empirical formula mass, and you're going to get some nice whole number. This one will never be, or should never be, a number with a decimal or a number and a fraction. So it'll come out to a nice whole number every time, so you don't have to have an extra step there. And then all you need to do is apply that number to the empirical formula. And when I say apply, you could think of distribute or multiply, whatever seems to make the most sense to you. So let's look at an example. A compound has an empirical formula of P2O3. So they've already done that process we did in the first part of this section. We also know it has a molar mass of 220 grams per mole. What is its molecular formula? So again, we want to take the molar mass and divide it by the empirical formula mass. So molar mass is given in the problem, 220, and P2O3 is our empirical formula. So if it asks us to find the empirical formula mass, I'll use my periodic table and add up the atomic weights 2 times phosphorus and 3 times oxygen. So why doesn't everybody take a second to find that? 2 times the number for phosphorus. Phosphorus is element 15. And then we need to add 3 oxygens to that. 15.9994 there. And I'm getting on my calculator like 109.9 something, approximately 110. And if you think about those two numbers, you probably shouldn't need a calculator here for this last step, because 220 over 110 will give us a nice whole number of 2. But 2 isn't your answer. 2 is what we're going to need to apply to this empirical formula. And so if we distribute that 2 or multiply through, our molecular formula is then P4O6. Now usually as soon as we write that, someone will ask me and say, well, Mrs. Hohenstein, that's not reduced. Why isn't it simplified? Well, keep in mind, a molecular formula represents a real compound, a real substance. And not all real compounds have formulas that are simplified. So for this one, for the molecular formula, it's fine if it's not simplified. If it's empirical, then it must be simplified. So to finish, I'll have you guys split into groups and work through one example of both of these together, a problem that incorporates both the empirical and molecular formula. And then once everybody's finished it, you guys can check it and see how we did. This problem is about nicotine, an extremely toxic and addictive compound found in tobacco leaves. I'm sure you've heard of it. Nicotine consists of 74% carbon, 8.65% hydrogen, and 17.35% nitrogen. So you should split into groups and determine two things. First of all, letter A, what is the empirical formula of nicotine? And B, if its molar mass is 162 grams per mole, what is the molecular formula of nicotine? So go find a group, everybody get up, move around, find somebody to crunch numbers with, and then come on back and we'll take a look at the answer. All right, letter A first. What's the empirical formula of nicotine? So our process, think about your poem, percent to grams, grams to moles, divide by small, multiply till whole. So we'll start with 74 grams of carbon, 1 mole of carbon, 12.011 grams. And we have 8.65 grams of hydrogen. Its atomic weight, 1.0079 grams. And nitrogen, 17.35 grams. Its atomic weight, 14.0067. So we'll start by finding the moles of each of those. 74 divided by 12.011 and 6.16 moles. 8.65 divided by 1.0079, you'll get 8.58. And 17.35 divided by 14.0067, you'll get 1.24. So when we get to divide by small, we'll be dividing by each of those by 1.24. And clearly the nitrogen will be 1. The carbon, you get 4.967. That is pretty darn close to 5. For hydrogen, you get 6.9 something, which will be close enough to 7. So this time we don't have a number that's, 0.5 or 0.25 or 0.33 repeating. There's no recognizable fraction here. They are all close to whole numbers. So this time we don't have the added step of multiply till whole. So our empirical formula is C5H7N. That's letter A. And then letter B, we need to take the molar mass, which is 162, and divide it by the mass of that empirical formula that we just determined. So if you take 5 carbons plus 7 H's plus an N, you should get 81.117. And when you divide, that gives you a whole number of 2. So if we apply this 2 to that empirical formula, we should get a molecular formula of C10, H14, N2. This brings us to the end of section 3.5.